time to start recording then. Great. Show started. Welcome back. Happy Thursday. Happy middle point of the semester where we're all trying to figure out which fire to put out first. At least that's how I'm rolling these days. Hello, Tova. Hello, Zoomers. All right, let's see here. I don't think I have any announcements. Next Thursday, we're going to be on Zoom only. I said that last time. By Tuesday, I will have some new materials up for you. I'm working on them. They're actually a very much updated version of something I did last time on crossed classified models. So when you have nesting in more than one way at the same time, that's what the next little sort of mini unit is. For today, we get to finish up example 4 and lecture 4 and deal with the second variable in the story, which we had not yet seen. That sound about right? Yeah? Any questions or things I'm forgetting that we should talk about before we dive in? All right, I'll take that as a no. So just to remind us, the single predictor variable that is going to be in our models is we're predicting 10th grade math outcomes in an actual data set of students nested in how many schools do we have in this one? 94 schools. And we're looking at the extent to which lunch disadvantage as a proxy for socioeconomic student status at the student level predicts math scores, where you can pay full price for lunch, which is 69% of the sample, get a reduced rate, which is 8.7%, or get free lunch entirely. So I'm thinking of this as an ordinal measure of disadvantage. Up to this point, we have played with this version of the predictor in which we just are tracking who pays versus gets some kind of discount, and that tends to be, I think, how it's used in practice a lot of the time, because there may not be that many people in the reduced category. But that is an empirical question, the extent to which you can lump free and reduced lunch kids together. And so I'm testing that in the second half of this example by adding this variable, which is going to change the interpretation of what the first one meant. So when this is all by itself, what does it mean?
So you have everyone who plays full price on the one side, and then in a group combined, you have people who get some kind of discount, whether it's just discounted or entirely free.
Exactly right. And so then once this predictor is added in, this predictor lumps together paid and reduced against free. So when they're together, the first predictor then becomes paid versus reduced. The second predictor picks up where that one left off and is reduced versus free. So I like doing it this way because I think it's more useful in ordinal variables to get the sequential differences between the categories than to compare each back to some reference category. But as long as you've got two predictors to differentiate three groups, you can set it up however you'd like.
So, question, and maybe I'm missing the point with this, but if we have three groups, is it smushing if we combine any of them, like at any point, or should it always just have been the three groups?
So I wouldn't use, so the question was, if we have three groups and we don't distinguish all of them, is that some kind of smushing? And I wouldn't use that word because I'm going to reserve that word for the conflation across levels.
Okay.
But I would say, yeah, you are making an assumption that the groups you've lumped together do not differ in their outcome, and that's always a testable assumption. I considered for about a couple minutes an alternative coding scheme by which the interpretation of the first one would stay constant. I considered doing something like this, where we have minus 0.5 here and positive 0.5 here, because then the interpretation of this one is paid versus the average of the two, and these two step in to differentiate the two. But then I got into the world of cluster mean centering with this, and I got really twisted in terms of what 0 is then, and I thought, nope, if I can't do it, I'm not making them do it. So we just stuck with 0 and 1. You're welcome. Yeah, even I look at my stuff sometimes and I'm like, this is ridiculous. Just stop it. Don't make this harder than it needs to be. But that is an alternative if you wanted to maintain it so that this stays the same meaning no matter what. That coding scheme would result in that constancy. Okay, So we're on page 9-ish, maybe 12-ish, somewhere in there, 10. So we re-went over last time, the first half of the handout, and we got to, let's see here, 3A for instance. After we added a random slope, we added a cross-level interaction between the two halves of this lunch variable. And we discovered that that cross-level interaction was smushed because we are multiplying the original paid versus reduced and free variable. That means a cross-level interaction with only that part is going to say that the within school effects of lunch are the same as the between school effects of lunch in terms of how this variable is moderating them. So moderation of the within and between effects to the same extent. That's what this is saying. So to fix it, we then added the quadratic, and that's where we got, I think that's where we all lost our wills to live, and I promised to let us go and we can try again the next time. Does that sound about right? Fair? Yeah, even me. This stuff is hard. So if we look at what's in the story here, I have beta 1 attached to these things. So gamma 1O is the main effect of student level paid versus reduced or free lunch. Gamma 1.1 is the interaction of the school composition of that variable with the level 1 variable. So this is both a cross-level interaction and a intravariable interaction, I would call it, between the two halves of the same variable. Beta 2 is only in here for the random slope that goes with it. So I had to cluster mean center the predictor so that I could ensure that the random slopes refer to between cluster differences and the effect of this variable and not have any of the composition stuff happening in that. But then to unsmush the cross-level interaction, we added this quadratic term here. Does that sound about right? Maybe. Okay, let me go back a minute here, get the logic down. So if I put in my original x here, so we have like our binary x predictor into the model, the slope that it would get is smushed, right? So if I add in, I take my same binary x predictor and insert here, and I add in the cluster mean of it, right? That fixes it. So this becomes within. What does this one become? Contextual. How do I get to between? You gotta say it the right way, though. Oh, well, I'll leave that to you. Okay. Anyone else? Add 'em up, add 'em up, fire. Okay, so we can agree on this, right? These are main effects. So if I add some stuff to my model, bivary, binvary. Let's try that again. Binary. This is when it's time to cut my nails, when I can't type anymore. Binary x times some moderator. Put that in here. What's that thing?
Smushed interaction?
Yeah, it's a smushed interaction, which means within by mod equals between by mod. That's what I mean by smushed interaction. So then to fix it, the rule is whatever you do to the level 1 slope, you got to do to the corresponding level 2 slope. So what do I need to add then to the story?
The cluster mean of x.
Yeah, cluster mean x times my moderator. Then, need some extra spaces in here. Borrow that. Then this one is within by moderator. This one is contextual by moderator. And can you guess how I'd get to between by moderator? Up, 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 add 'em up, up, up. Same idea, different level of complexity. So this all makes reasonable sense, maybe? And then here's what I'm going to do to you. Moderator is CMX. So if I follow my same rules, that's where we end up with the quadratic. Whatever you do to the level 1 slope in terms of adding interaction terms, you got to do to the corresponding level 2 slope if you're using this method in which the original level 1 predictor has all the information in it. It hasn't been partitioned into just its within self. What if we had done it the other way? Do you want to go through that real quick? Sure. Okay. So if I swap this out. Oh, can I do it side by side? I can try. Okay, I can try. Hang on. Where is the little thingy? I need that to stay. We're going to wrap this column of text. Maybe, and then we'll squish it. Okay, yeah, we can get, I can try side by side. Okay, and let's see here. If I do x minus CMX, so then if I put that in the model by itself, what do I get?
Smooshed. That's the cluster mean center.
Yeah, this is the cluster mean centered version. So if I put this variable in the model, what do I get?
Within.
This is within. What if I put it in and I add the cluster mean? Then what is it?
Within.
Within. What is it no matter what I do? Because you took out, there's no worrying about smushing because you took out the between. Like it only has within information, that's all it can do. Now what's this one?
Between.
Yeah, this is between because it doesn't have, like this variable has no information in it about level 2. So contextual is the extra information provided by level 2 that's not already in level 1. None of the information is in level 1 when we do it this way. So if I do my cluster mean centered x, do order of operations, very important here even when you're pretending, times moderator. This is what?
Cross-level interaction unsmooshed.
Cross-level interaction. Is it smushed or is it okay?
Okay.
What makes you say that it's okay?
Because you are considering only the within part of your predictor.
Yeah. Again, all it has is within. So this is the only thing it could possibly be. And if I add in the same thing along with the corresponding level 2, then same or different?
Same.
Same. What's this one?
The level 2 interaction.
Yeah, this is between by mod. You don't have to, in the sense that if you leave a smushed interaction in, you're saying something. It's not that the level 2 part is 0, it's that it's the same as the level 1 part. Here you don't have to, but I think it's weird not to. Because what you're saying with this variable is that the effect of having more of x than everybody else is moderated by some other thing. But then how much x everyone else has, I feel like also needs to be moderated to be this, like the second half of that story. But if you test this interaction and it's 0 and you want to kick it out, fine. There's nothing mathematically wrong with that. I just think it's sort of weird to interpret that way.
Lisa?
Yeah.
In the second case, the cross-level interaction would be reducing part of the random slope variance. However, the level 2 interaction would be reducing part of the random intercept variance, right?
Yes, yes. So in terms of effect size, cough, cough, formative assessment question. If I put in the cross-level interaction, it reduces the random slope variance that goes with that predictor. And it's two different versions of the same predictor here, technically, but they're working as if it's one thing. Because what this variable ends up meaning is just within. So you can think of this all as part of one equation conceptually. So the cross-level interaction explains why there are school differences in the disadvantage related to student lunch. But the quadratic interaction, the level 2 interaction goes here, which means it explains U0. So level 2 interactions explain intercept variance. Level 1 interactions would explain residual variance. Cross-level interactions, it depends. And that's the final piece of lecture 4 we haven't talked about yet. If there is a random slope in the model that is associated with the level 1 predictor in the cross-level interaction, that is what gets explained.
Sorry, say that again.
Yep.
Maybe 5 more times, I don't know.
Yeah. Hang on, my working memory buffer is emptying. I gotta get it back. Okay. If there is a random slope in the model, the cross-level interaction between the variable that the random slope is for would explain that random slope variance. So if I have a random slope for x, and I put in moderator by x, it explains the x random slope variance. But if I have moderator by z, it would not, because z is a separate thing.
Would explain random intercept in that example, or?
If z were level 1, no. Yeah, we're getting to that, actually.
Great, I'm not gonna ask any more questions.
Okay, yeah. I have an example of that, because that's how it worked out in this data set.
So, what, can you explain, so you would use the grand mean centered version for interaction stuff if you wanted contextual slopes, or if it was like a weird interpretation way of doing it otherwise? Like, why would you do this extra headache?
Great question. Possibly rhetorical. Why would you do this extra headache? I'll end on that. So yes, why would you use this version of the model where you have a headache? For exactly the reasons that you said. When what you want is contextual effects as direct model parameters, like you want to talk about them, moderate them, see what explains them, that kind of thing, and or you have an x variable that cluster mean centering would be weird for, like a binary variable. But I agree with you that this is more straightforward, and you could still get contextual effects. How do I get a contextual effect out of these two?
Between minus within.
Yeah, between minus within. I don't have a song for that. Same thing here. Contextual moderation would be the between by moderator minus within by moderator. It's the same principle. And yes, I like it this way. The rest of the world does this. Up to you. And if you're going to analyze your own data, which many of you are, I was excited to see that, you can choose. You can choose which way makes the most sense to you, seems the most useful. So long as, if you are going to go over here, the random slope needs to be with the within version. Otherwise, that's a different kind of smushing that will be nearly impossible to solve. All right, not that one. I wanted that one. Okay, does that help a little bit? Okay, other questions or things you want me to say again? I'll try my best.
So with our data,
Mm-hmm.
is there an estimated time frame as to when we might find out if, yay, go ahead with it, or?
My goal is to have everyone's feedback to them by Monday, along with the rubric of what's expected for your assignment, and then the ChatGPT folks. I hope to have that done by then too, but maybe not. That one's going to take longer. But yeah, this is not meant to be like a term paper. This is not a thesis. This is just to be like the scope of a regular homework assignment. So a couple models, a results section. Yep, but I will give you more specific instructions than that, and the point breakdown for each. That's helpful to me when I'm grading. Just try to be empirical.
Yeah.
Yeah, I hated it in college when like I'd turn in a paper and I'd get something like B+ on it and no feedback beyond that. It's like, well, it's not good enough, but I don't know why. Like, what am I going to do with this information? So I veer the other way. I'm like 1.75 out of 2 because you didn't do this. That's how I roll. But that's useful, right? Like, that's prescriptive, as we would say. Anywho, so we are unsmushing the cross-level interaction by adding the quadratic term, following the rule that whatever terms you add with respect to the original level 1 predictor, you have to add the level 2 equivalent. So because we added this interaction of the level 1 predictor times the contextual effect, we have to do the same thing at level 2. And R, when I had the output, rearranged the output in a different order, which made me angry, but I couldn't figure out how to fix it. And I spent like an hour trying and gave up. So if anybody knows how to make R, like, do it in the way that I wrote it and not the way that it wants, please let me know. I would be very happy to get that suggestion. And I think we were talking about the pattern of relationship here. Do you want to go back over that a bit? That'd be helpful? Okay. So we just decided that because this is the confusing way to do this, we have within effects and contextual effects, right? So that's what these two are. PVRF is the level 1 predictor in its original binary form. And then we have the cluster mean of that variable centered at 0.3, which was the average for the sample. So within the same school, a kid that gets some kind of discount on average will do about 9 points worse. And that is specifically when the interacting variable is 0. So a poor kid will do about 9 points worse in a school where 30% of the kids are poor. What happens to that lunch-related disadvantage as you get more poor kids?
Less negative.
This is a less negative. So does the effect get stronger or weaker? Weaker. Yep. If the answer to the question is less negative or less positive, that means weaker. If the answer is more positive or more negative, that means stronger. So the disadvantage is reduced by 5.3 for every 1 unit change in my moderator. That 1 unit change corresponds to a proportion of 0 versus 1, which is weird. So we can move the decimal over to make it less weird. So for every 10% more poor kids, the disadvantage, the slope itself, becomes less negative by 0.53. And that is marginal. But stay tuned. Stay tuned. Okay. How are we doing so far? Good?
So, within this data set, having the discounted poor kids, whatever, kids who get some kind of discount, brings your score down.
Yep.
But then, and granted it's not significant, but then somehow the more poor kids you have, it makes it less.
It doesn't hurt to be poor in schools where there's more poor kids as much.
Okay.
It's
I
the
got it,
difference
okay.
between the rich kids and the poor kids shrinks. But that doesn't mean that going to a school filled with poor kids is not its own thing. That's what these terms are doing right here.
Right. Also, just to be clear, not a value judgment,
No.
just trying to understand that, trying to understand the logic.
No, there's enough words in here that I can't keep saying lunch-related disadvantage. I'm just going to say poor kids, all right? Are we okay with that? I know that's not accurate, but I just need a shorthand because this is hard enough. So, being a poor kid, not good for you. Less not good for you if there's a lot of poor kids in your school. But if there's a lot of poor kids in your school, that's its own problem. So for every 10% more poor kids there are, the school's mean math goes down by 1.8. And that is specifically at 0.3 for with respect to the quadratic, and it's specifically for kids who pay for lunch with respect to this. So this variable is involved in 2 different interactions simultaneously, so it's conditional on the 0 value of what it's interacting with in both cases. That means it's the slope of the line that's tangent to the curve at 0.3, and it's specifically for kids who pay for lunch, because that's when that one goes to 0. Do I need to get paint out again? Can you all picture the cliff? Is it this way? That way. There we go. I can't, my elbow's gonna break. I can't do it that way, but you know what I'm saying. So this is negative. It becomes non-significantly more negative as you move up the variable. So the contextual effect sort of accelerates, but that's not significant. The other way to think about it is the difference in the contextual effect among kids who get free lunch. That difference is reduced. So it's the same pattern both ways of a less negative coefficient. And relative to the previous model, the smushed cross-level interaction was 3.9. Once we unsmush it, it goes to 5. The reason that it was smaller before is because this one was bringing it down. That one was stuck in there, and that's why it's pulling it down to 3 when it really wants to be 5. So the cross-level interaction should have explained the random slope variance for this variable. The level 1 variable, the random slope is 4. Cross-level interactions explain its slope variance. So why is it that there are school differences in this lunch-related disadvantage? Well, part of the reason appears to be related to school composition. The new quadratic interaction, what's that going to explain again? What's that targeting in terms of piles of variance? There's 3 to choose from.
The random intercept variance.
Yeah, that one's targeting random intercept because it's an interaction between 2 level 2 predictors. So altogether, level 1 predictor is targeting residual. The linear and quadratic contextual effects are targeting random intercept. Cross-level interaction is targeting the random slope for the level 1 predictor in the interaction. Every predictor has a job to do. Watching the variance piles move around is not nearly as clean. It's sometimes difficult to tell, but theoretically, that is what should happen.
Lisa, can you actually go back up? I just
Yeah.
want to walk through conceptually
Mhm.
kind of what this model. So we're looking at paying full price versus some discount for being entirely subsidized.
Yep.
It's a smushed variable. So we have a level 1 predictor, a level 2 predictor. That's the first 2 lines.
That's right.
And because it's a cluster mean centered, it's a contextual effect at level 2.
Correct.
Because we're dealing, now we want to test an interaction. Because it's smushed, we need to have essentially a level 2 interaction and then a level 2 and a level 1 interaction.
Yeah, if you want the cross level, because you set up your model this way where the level 1 predictor has the both in it, then you need the level 2 interaction to unsmush the cross level interaction. Yep, in the same way that you needed the contextual effect as a main effect to unsmush the level 1 slope. Same is true for any moderation patterns.
Thank you.
Yep, thank you. Okay. All right, any other questions? So if you want to get the add 'em up, here's the contest 1Ds to do that. So I have a simple between slope that is the sum of these two. Simple meaning conditional on the moderators being 0, not that it's easy. They should actually be called complex slopes, as you know. And I also have the level 2 interaction, which is those two added together. Same thing. Here's some pseudo R-squares. We can compare the smushed model here, where the slope variance went down like it was supposed to. So 2, is the slope variance in this model. The intercept variance went up. That's the smushing contribution. It actually made more variance because the wrong effect at level 2 was in the model with respect to the moderator. Once we unsmush the cross-level interaction, it goes back down to where it's supposed to. So all in told, it looks like the level 2 model, we explained another 1% of the random intercept, another, looks like in total about up to 7% of the random slope, and no more of the residual, because we're not focusing on that right now. But we have the other binary predictor to consider. So is there a difference between the kids who get a discount or free? That's the next layer. So that's where I have a new predictor, beta 3, paid, reduced versus free. So that's the one that goes 0, 0, 1. The first one is 0, 1, 1. So what do you think? Let me just ask you. Do you think there's going to be an effect? Do you think there's a difference between, in your math score, of getting a discount versus free lunch?
Yes.
You think there is? We're going to vote yes? Okay, let's find out. So I went ahead and unsmushed it for the sake of time here. So I put in the contextual effect that goes with it. That proportion I centered at 0.19 based on the means in the data.
So what's the SM?
School mean. Yep. Yeah, I went SM today. I probably could have done CM. My bad. I can go back and fix it.
I mean, as long as I know what it is.
SM is school mean. Yep,
And then I have another question.
yes.
Can you go back up? So, for beta 2C, that's the interaction.
Beta 2, this is the random slope that goes with the cluster mean centered version of the first binary predictor.
So I guess my question is, like, why is beta 2C a random slope, but beta 3C gets a gamma?
So beta 3 right now is, so this is another variable that has the level 2 part in it. It only has a fixed effect in this model so far. So this beta 1 having the gamma is parallel to this beta 3 having the gamma.
Because beta 2 is really still about beta 1.
Yes. Yeah, beta 2 and beta 1 are in cahoots. Okay, they are working together to create the first set of differentiation of paid versus not paid to some extent, and the contextual effects that go with that. It's just that we can't estimate the random slope for that version of the smushed variable. It has to be the within version. So this is called a hybrid model because we have these two different versions of the same predictor, one on the fixed side, one on the random side. And if you don't like it, then you can cluster mean center everything and stay internally consistent. That's your alternative choice. But for binary variables, that gets a little weird. That's all. I don't have a problem with it, but it does get tricky, right? Yeah,
Yeah.
it gets tricky. Especially if you go to weird coding schemes. Then it gets even trickier, but okay. There. All right. Are we good to go? Keep going? Maybe? Yeah, you're right, because I did it in the code, it's CM, and then here it's SM. I should fix that. I'll fix it. So we're adding in a level 1 within effect, differentiating reduced versus free, and the corresponding contextual effect, which is the proportion of children at that school who get free instead of reduced. And at this point, I knew we would be very tired, so I just started highlighting new things.
That's appreciated.
That's just as much for me as it is for you. Like, where are we at? Especially when you have these variables that all look the same. So the first new effect here is the within school difference between kids who get reduced versus free. The previous effect has now changed its interpretation as a consequence. So P versus RF is paid versus reduced. The new variable is reduced versus free. And so yeah, this was like 8 something before. Now the total discrepancy to get up to free is even larger, but there is a difference and it is significant. So yes, those of you who guessed that it does matter if you get reduced versus free, you're right. I know. And it's almost the same size, which to me was like, what? But it does. At the individual level, it absolutely matters. At the contextual level, not so much. So there's no additional contextual effect that is significant with respect to the proportion of students who get free instead of reduced lunch.
The interpretation of the previous one, though, changes a little bit.
It does. Yeah, this one is paid versus reduced now, specifically.
But reduced versus free doesn't.
Yep.
In terms of level 2.
Yep, so paid versus reduced is minus 22. Reduced versus free is positive 6. So it's actually in the opposite direction you would expect. Math scores are higher in schools that have more kids who get free lunch rather than reduced.
In a school where there's more poor people?
There's 2 flavors of poor now.
So
this is like a little bit poor, and this is more poor.
Right.
Poorer.
So I'm saying so in a school where you have, so in a poor school altogether,
Mm-hmm.
when you have more kids who get completely free lunch, the math scores are better.
Yeah.
Okay, all right.
Non-significantly, but that's the pattern.
Just wanted to make sure I was following.
Mhm.
Which,
Yeah, so the contextual effect is even stronger after you differentiate. So it's paid versus reduced that seems to be the important part. Reduced versus free is a non-significant difference from that point.
can we model there? Maybe we get to it where you have a school that's just like all paid.
I don't have a model, but I've got a picture. Yeah, at the end of this, I was like, I have no chance of interpreting this
Okay.
without some pictures to help. So pictures are going to be very important.
And
So-
this is real data?
This is real data.
Okay.
Yes, it is. The only thing I did to it is filter so that I had at least 31 kids in each school, so that I had a decent way to estimate, what the proportions were. So which fixed effects have changed? Like most of them. Is the answer. Yeah, I think actually all of them have, because these two are now specific to paid versus reduced. These two are paid versus reduced, and these are reverse versus free. The only thing that hasn't, I think, oh, no, it still has. It has, because we added this one. The intercept changed too, because this is not just a school where it's 30% free or reduced, but it's a school where like 19% is free and the remainder are reduced, 11. So yes. Now, do you think that the extent to which reduced versus free matters, do you think that varies over schools? Is that an empirical question? What am I talking about when I say the extent to which this slope varies over schools?
Random.
Yeah, other one, random. Yeah. Are you laughing at me?
No, when I
'Cause-
hear whispers on this side
Yeah.
of the room that it's right, I acknowledge that they're right.
Yeah, you can like tell them to talk. Yeah.
Yeah.
Don't whisper. It's better to be wrong than vague. Whispering is vague. Yes, it is. Yep. So here's what we got. Now we have the same weirdness with respect to one variable carrying the fixed effect and the cluster mean centered version carrying the random effect. So now we've added beta 4 to the story here to do that. And U4 to go with beta 4. So random slope. So this is the first time you've seen a model that has two random slopes. We have in Stata, it looks like this. We have intercept that's not written, and then two slopes. So if I add a random slope, how many parameters am I adding to the model?
3.
Yeah, so it's the variance is 1, right? Now what are the two that are less obvious that we're adding?
Covariances.
Yeah, the covariance with the stuff that was already there. That's what it ends up being. And Stata says, okay, this is not a model. If you get this, stop. It gave up. It's like, yeah, I don't know. I have no idea. Dots are bad. Dots are bad news in any software. If you get dots, it gave up. So these are the values at the last iteration when it was trying things on and trying to make the data taller, and it got through the maximum number of iterations without ever hitting a point where it decided what was tallest. So it just spit out the last try and said, good luck. In R, we have the same thing here, so new random slope, and R's like, I got this, it's fine, except when you go down here and then you see this. Does 0 mean okay, Vladimir?
No.
I don't understand this error message. Boundary, singular, see help is singular, code 0, okay. It's fine.
No, that means that there's 0 things that are okay with it.
I am not okay. My okay level is at 0.
Lisa, I've gotten that before, and usually it's when when there's no degrees of freedom.
Yeah, so it tried, and based on this output, it doesn't look like there's anything wrong, because I have I don't have standard errors, and I never get that, but I do have correlations that are within the boundary, right? So that's one of the things, when things break, look for correlations among your random effects that go to 1 or -1, because it traps it between that. So if you get that, that means it hit the wall. And this number is not 0, it's there. So this is not terribly helpful in diagnosing what the problem is. For a point of comparison, I have the SAS output, and this is what SAS gave me. So for the new slope variance dots, again, it doesn't know what it is. It thinks it's 0 to 16 decimal places. And if you look at the correlations among the random effects, the correlation between the two random slopes is 1, and the correlation of the second random slope with the intercept is -1. It's like, yeah, I have no idea what this is. So if you start to see this stuff, that means you've probably added too many random things and you need to simplify. I have a likelihood ratio test here that provides converging evidence that, yeah, the difference in height is not significant when I add this thing. And the fact that I'm getting dots where I should have gotten numbers is also evidence that I can't keep it. I have actually seen it happen where the likelihood ratio test is significant and I get dots and zeros. I have seen that happen. So my general philosophy is if you see dots, stop. You don't get to keep it. Question?
So does that mean that we have to get rid of beta 4C, our random slope variance?
Yes.
Because it's just not adding anything and it's breaking everything?
Yeah, that's correct. Yeah, the model cannot support a second random slope. It's breaking it to some extent. And it looks like there's no evidence for heterogeneity across schools in that slope. That's how I would interpret it.
So then if you were to flip it, if we had done this random slope instead of the other one, why choose beta 4?
Well, everything was fine when it was the first random slope that we had, and it was adding the second one that broke everything. So that's why I would think it's the second one's fault.
But would you come to potentially different substantive conclusions if you try,
Like the opposite order?
yeah?
Yeah. In theory, it could be the case that the model will only support one, and you can't have both. But which one you have is maybe debatable.
So you would probably need to run more models and test some things and see what came out as being ultimately polished.
Yes, if you can only keep one, then going down the path of which one should it be. Now, I will tell you a couple ways to think about that. One is that a model that has one random slope and then versus the other, and all the fixed effects are the same, is not nested, but you can use AIC and BIC to see which one is taller for that, see which one it likes better. Another important factor is what else is in the model. So in our current version, we have the cross-level interaction with the variable that goes with this random slope. So we need to keep that one. I don't have anything predicting the second one yet. So Tolga says overloaded, yes. And this is the point where somebody would say, but doesn't Bayes fix it? And I would say not necessarily, but it might be worth a shot.
Yes.
I knew you were gonna pipe in there. Yeah, the way that Bayes would fix it is if you put a more informative prior on what the slope variance would be, but then you have to defend that as a way to make the model work. So there's no free lunches.
So,
Yes.
Lisa, we can keep one random slope for one of the indicator variables we are using.
Yep.
So, for example, if we have one categorical variable with 5 predictors or 5 categories and we are using 4 slopes, to test the random slopes for that variable at level 1, should we include the 4 random slopes in the model or test one by one?
If you have the sample size, you could try all 4.
Okay.
But otherwise, the interpretation of what it means depends on what it's paired with. So like in this model, this random slope is specifically paid versus reduced, and this one is reduced versus free. But without it, then it's paid versus either.
Yeah.
So you have to be careful with what the one is and what's being lumped together if you leave certain things out.
Okay. Good.
Okay, so this model is broken. We don't want that. So the last model, I promised. So even though let's see, oh, I left it in here,
Yeah.
typo. Even though I took it out, like I just did, beta 4 is gone. I'm still going to test the same pattern of interactions with respect to a cross-level interaction and a quadratic interaction of these two new variables to see if they contribute anything. But I'm going to have to introduce you to a new vocabulary word in order to do so. You can moderate a slope that doesn't have a random slope. Then you would call it not fixed, meaning everybody gets the same, not random, meaning every cluster gets their own, but something in the middle that is known as systematically varying or non-randomly varying. So I have some slides about that as a concept. This is an example of that concept. We'll do the slides in just a second. So what this model is saying, because I took out the random slope, is that clusters don't vary randomly in the effect of reduced versus free, but they are allowed to vary systematically as a function of this moderator only. So it's like a happy medium. Not everybody gets the same, not everybody gets their own, but somewhere in the middle. Deterministically varying as a function of this covariate only. And so that one's not significant. The new one's not significant. But look, our previous cross-level interaction has crossed over. Hooray! But I don't like this model. When you start to see standard errors of 32, it's like, I don't know. I didn't get any error messages, but this looks sus to me. That's a technical term. The degrees of freedom look really sus too. It's like, you can't have degrees of freedom of 12,000, I'm pretty sure. So, yeah, it's all messed up. So I have like what you would have done had the messed up not happen in terms of decomposing this into simple between and level 2 between interactions for each of the variables and stuff like that. But I don't like this model. We're not going to keep it. So the model that I chose to interpret is the one before we added the random slope and the two interactions. And in that one, the cross-level interaction just eked under 0.05. So we're going to have some pictures to talk about that. Yes, sus. Last year, Hugh was an Among Us character for Halloween, so we had to hear about sus all the time. It's sus, mommy.
But
Yeah.
did he use it properly? 'Cause
He
my
did.
kids use it like to mean anything they want it to mean at any given time. And
Yeah.
I'm like, that's not the definition. They're like, yes, it is. And I'm like, okay, I don't know what to do.
No, we realized he knows what it means when he was talking about Santa Claus and the Tooth Fairy. And I don't want to spoil it for anyone, but they're not real, okay? He's like, Mommy and Daddy were acting all sus about it, and that's why I don't think the Tooth Fairy's real. It's like, that is correct. And now I have like a Ziploc baggie of baby teeth that I don't know what to do with.
You have lost some.
Like, I was like, do I throw them away? Like, that seems, it's creepy to keep them and it's creepy to throw them
Yeah.
away. I'm not really sure what to do. But,
Black market stem cell research.
ooh, that is dark.
I mean,
Yeah.
Does it pay money?
There's a market for used baby teeth? What?
You might want to open like an alternative browser through a VPN.
Good, okay, pro tip, go
Not at work,
incognito.
yeah.
Oh my goodness. So yes, before we get to the pictures, let me do just a couple on this here. So the systematically varying vocabulary word. Slide 38 out of lecture 4 here. So this model is not the craziness. This is just a generic within cluster-centered X. I've got my cluster mean here for the between effect. I've got a intra-variable interaction here and a random slope. So then the question is, am I allowed to test this cross-level interaction without this random slope in the model? That's the question. So what this model is saying is that the effect of within cluster X varies randomly over clusters. That's what the blue thing here is. And that part of the reason why it varies over clusters has to do with whatever this cluster composition is, cluster mean of X. So then you're in a tricky spot. Let's say that your entire point of your dissertation is this cross-level interaction. You are going to test it come hell or high water, another idiom. If you find out that the random slope is not initially significant, are you done, or do you get to go ahead and test it? And people fight about this, and there's two different perspectives. Some people would say, nope, you're done. The logic is, if there's not enough of a signal to add U1, if there's not evidence of cluster differences in the effect of this predictor in the first place, how are you going to predict those non-differences? The model is saying this is a constant. How are you predicting variance that doesn't exist? And to the extent that the variance of U1 is there at least a little bit, even if it's not significant, you will end up with higher type 1 error rates than you should for testing this cross-level interaction. The rest of us say, well, maybe not so fast. Power to detect random effects is not necessarily the same as power to detect fixed effects, particularly if you have a small number of clusters. It's possible that saying I don't have a random slope would be a type 2 error. And so from that perspective, maybe testing the cross-level interaction anyway after you do your due diligence and testing the random slope first might be okay. But if you want to do that, then we have new vocabulary. So let's say we have a couple different scenarios here. Let's say that I have a fixed slope at level 1. So I have a within school effect of something. And I'm interested in seeing if that within school effect varies by some kind of level 2 group, like private versus public school, something like that. What can happen if I test that cross-level interaction as a function of what happened with the random slope? So let's say that I first tested my random slope for within cluster X and it's not significant. If I go ahead and test the cross-level interaction, then I would say that the level 1 slope for within school X is systematically varying. It is varying systematically as a function of group, but not randomly. So that would mean that public schools get one slope, private schools get another, and that's it in that example. If it were not significant and I kicked out the cross-level interaction, I would stick with the word fixed, meaning every cluster gets the same within school slope. Second scenario, what if you had a random slope? So it looks like there were differences to be explained in this within school effect, and it became not significant or even 0 after adding in the cross-level interaction. Would that be a good thing or a bad thing? So I had a random slope, I put in a cross-level interaction, and the random slope variance that was left over is 0 or very close to it. Think that's good or bad? This is a finger question. Doesn't make sense? Don't understand the question? Okay. Let me see if I can phrase it in a way that's more direct. So we thought we had cluster differences in this within school slope. We added in a predictor that we thought was one of the reasons why. And the U1 variance that was left over after this goes to 0. Doesn't randomly vary anymore. Anymore. So we thought we had cluster differences in this slope. We put in something to explain them, and they all went away. Does that sound good or bad? That would be like a slope R square of 1. Explained it all away. So good. Yeah, that can happen, and I've seen that happen too. If there's not a lot of variability to begin with, and you put in a cross-level interaction to explain it, and the variability that's left over is 0, then you've explained it. Like your model basically says, I know all the reasons why the slope varies across school. It's because of that thing. And after I control for that thing, there's no more random slope variance. Question from the Zoomers, wouldn't it depend on what you were looking for? Potentially, yes, but if you're putting a parameter in the model, it's because you want it to be there, in most cases. Unless you want to prove someone wrong or something, but that's a different aim. So that scenario, then, it's systematically varying as well, because the random slope is gone. It's been explained. If the random slope was there, and it sticks around after you add cross-level interactions, then we would just call it random.
In the middle case,
This can't happen, that's why it's a dot thing.
yes. So this is more like a how you would talk about potentially the results you get based off of kind of like your significance pattern and whatnot.
Mhm.
I think it's a question for me of like, are you reporting then the model that still treats that as a random slope? You're keeping that in,
I would.
yeah.
I would. I've actually done some simulations to look at this, and if you kick it out, like, and it's still not completely zero, then the type 1 error rates go haywire. Like, you need to keep the little bit that's left if it's detectable. But the fact that, like, if you do a likelihood ratio test and it says, it's not significant anymore, then conceptually you could make the argument that you have explained all or nearly all of the slope variance that was there with your cross-level interaction.
So you're saying keep,
I would.
I want to hammer home,
Yep.
keep the random.
I would keep it.
slope.
I would keep it unless it goes to zero and causes dots. Yeah, if it causes dots, then it needs to go. Yep, but that would be part of the story. So, in terms of vocabulary, level 1 slopes can be fixed, meaning all clusters get the same. They can be random, meaning all clusters need their own, or they can be systematically varying, meaning they vary as a function of known characteristics, but not randomly otherwise. Level 2 predictors can only be fixed, systematically varying. Technically speaking, you can have a level 2 random slope, but that's not what it means. It's intercept heteroscedasticity instead. There. Okay, so now I have some slides about variance explained. Cough, cough. Formative assessment question. But let me go back to the model here for a second, because I can illustrate this much more simply. Do you remember the rule about what predictors are supposed to do with respect to their variance? Within cluster X, what does it explain? Yeah, the one in this row. Cluster mean X, what does it explain? The one in its row. What does this one explain? The one in its row. What if this is not here? Ooh. Level 1. Yep. If there's not a targeted variance component, it goes back out of level 1. So a cross-level interaction will explain residual variance if the level 1 part of the interaction is fixed only. It will explain the random slope variance that goes with that predictor if it has one.
Can we make like a flow chart? What sort of predictor do you have?
Yeah. Well, that's sort of what I was trying to do. Like, level 1 predictors and interactions among level 1 predictors would all go in here. They explain E. Level 2 main effects and interactions among level 2 predictors would go in here. They all explain U. If I have a random slope, any interaction with the predictor, the random slope is 4. We'll explain that one. But like if I added within cluster X2, and I have an interaction with that, that doesn't have a random slope in the model. It would have to come out of E. The random slope came out of E in the first place, so it's like it's still buried in there. So we'll talk about this on Tuesday as your formative assessment questions on variance explained, but this is where it is tried to summarize in terms of what happens to what. So, stuffing my slides with words so that you don't have to write everything down. That's the goal. There, I did it. Intermediate summary. The rest of this is on the video from Thursday. Okay. Now, what the hell do we do with this model? That's the question of the hour.
Throw it out.
Throw it out? So I threw out the random slope that had the dots. I threw out the weirdness with the standard errors of 32 or whatever. How about some pictures? Pictures are good. And this took a minute, believe me, because I had to think about what was logically possible. So here's some words, as usual. Here's my final model equation that I'm going to interpret. Here's a table. So if you provide your readers with an equation, for the love of God, do not use these symbols as your row labels. No, I can't even tell you how many papers that I've reviewed where literally this is all they give you and the numbers. Do not do that to us. It's mean. And do not, I know, and don't like take, and our, well, so if you have an equation, then you can tie the parts of the equation back to the words that they mean. And, you know, like the Jonathans in the world will ignore my words and just focus on this column. And the rest of us will ignore the gammas and focus on this column, and then everybody's happy. So I've got estimate, standard error, and then I have a p-value column here. I also have my variance components along with the symbol that goes with them. So that's a trick. Do not put U0 here. It's the variance of the U0s is the parameter. So that's why it's tau squared sub U0. Same thing with this. This is U2, and this is E variance right here. So then I have a narrative walking through all the terms in this model, and then I cry uncle and get to pictures. So here's the tricky part. We have two contextual effects in this model that differentiate proportion of students with respect to reduced lunch and free lunch. We need to make sure that when we plot representative schools, that those proportions still sum to 1. You can't have a school that has 70% poor kids and 70% not poor kids, right? That doesn't work. So I made several different pictures trying to sort of drill down into what this model meant. The first one is illustrating the contextual effect of students receiving reduced price lunch rather than paid. So all of these are holding constant the proportion of students who get free lunch. So 10% free for all of these lines, okay? On the x-axis are the kinds of kids that I have. Paid, reduced, or free. The lines are going down, that's your within school disadvantage. So they break in the middle because the first part of it is covered by the first dummy code, and after this breakpoint is the second dummy code. Okay, with me so far? So that much is constant. In all these pictures, the lines are going down. There's a disadvantage associated with being poor, and that disadvantage is almost as large if you're just reduced lunch or if you're free lunch. Like it keeps going. So in total, there's like a 9-point gap here. Half of it is 5. Yeah, here's the distinction. So this part of it is parallel because this model does not have any moderators of this half. The moderators are only on this half.
This is before we unsmush the interaction,
No, everything's unsmushed here.
okay,
So what's in this model?
sorry.
No worries. No. So, and note the way that I labeled these here, okay? So this is one variable. This is paid versus reduced. And here's the within effect, the contextual effect, the quadratic effect, and the cross-level interaction. And then this is the second variable, and we only have main effects here. We have a within effect and a contextual effect. So nothing is smushed in this model. But the second term is not moderated by anything.
Right, cool.
Yes.
I'm back to where I need
Yep.
to be.
Yeah, reduced versus free is the same for everyone. But paid versus reduced is not. Paid versus reduced depends on what kind of school you go to. So then the pictures are illustrating some differences here. So these are different kinds of schools. And inside, by the way, the Excel sheet that I started typing in are all these pictures and all the things that I made them in. So you can trace my logic of how I set this up. But I have the predicted values that are being plotted next to it. So the contextual effect is this difference right here. And it has to be this one because of the interaction cross-level term. So these are school differences as a function of the proportion of students who get reduced lunch instead of paid lunch, holding free constant. And the quadratic effect is the larger differences between the lines as you move down. It's very subtle, but like blue and purple are farther apart than red and green are. And you can also kind of see the differences in this slope as plotted here too. So it looks like the more kids that go to your school that get reduced lunch, the worse your school does. Same idea, but now holding constant the number of students getting, what is it? Holding reduced. So now we're varying free versus paid, and we see the same type of pattern. So the more free lunch kids you have rather than paid, the worse your school does. But this one, nice happy little rainbow plot here. This is free versus reduced, holding paid constant. And they're right on top of each other and actually backwards. Purple is the highest. So this is the contextual effect that was actually positive for reduced versus free, that was non-significant. So like all together, I would say that at the child level, yeah, it matters if you get free instead of just reduced. There's an extra disadvantage. But at the school composition level, that's not true. At the school composition level, it's just how many kids are poor. Like there's, regardless of which kind of poor you are. There. I get the sense I did not make it better, I made it worse.
So I'm curious then. So this
Yeah?
is from a paper.
No, this is from a data set. I don't believe this has been published.
Is it going to be published?
Not as far as I intend. Because this is just a class example. And I don't have as much information in the data set that I would need to control for X, Y, and Z other things, probably.
Okay. Then I don't have a question.
Oh, so, okay. All right. Was there another question? Did I see your hand? Where did I get these numbers from? I got these numbers from, you could do it in margins. I did it in Excel. I did it because I wanted to show you exactly what was going into everything. So the way that I have these set up, these are the fixed effects. And then these are the predictor values, where the ones that are not being used in the computation are grayed out. But I have them in here just because these are the original way I thought about it. So like this school has, 20% poor kids, 30%, 40%, 50%. And then the centered version of the predictor is what goes in the model. And so you have to have a value for every predictor that's in your model, and you have to decide what you're going to vary and what you're going to hold constant. So like this one, I held constant the proportion of kids that get free lunch. And then this is the formula. Constant plus slope times variable plus slope times variable plus slope times variable plus slope times variable. So if you're good enough at margins, you could make this work and have it spit it out for you and have it spit out a plot too. Same thing in R, same thing in most software packages. I just wanted to show you like literally the math of how I got through all of this stuff, where these things came from.
And then one other quick question. So this table 1, that's how you would expect it to show up in a manuscript. The gammas.
This is what I would do, yeah. Yeah. If you want like extra credit, like if you were going to throw the between effects in here, then you would have to say, well, the between effect is gamma 01 plus gamma 10. Like you would have like show literally the linear combination of the terms that created it, and you could add that in here as well. So I like this because it's taking some of the work off the reader, rather than just listing like this is the effect of, this variable. It's like, well, what does that variable mean? Let's do the translation for them. That's the contextual effect.
Yeah. As the role of reader, that is appreciated.
The number one rule in writing results sections is assume your readers have no working memory of any kind. None. Anything you can do to save them working memory load, you do it. Then they'll stay with you, even if it seems redundant. So,
Tell people what you're gonna tell them.
yep. And then tell them what you told them. Yep. Yes, indeed. But there's like several layers of steps of figuring out, like, what is this variable? What does it mean? Especially in a multi-level problem. And so explicitly labeling things as within and between and contextual can help your reader. Question?
Lisa, here we have not explored or analyzed the residuals in our model, but we assume that they are multivariate normally distributed at each level, right?
Yes.
Should we perform some kind of analysis in our residuals just to make sure that that's true?
You could try to output, you could create predicted values that involve the fixed and random effects so that you can get the ease and look at their distribution and stuff like that. I would say that the extent to which that would be a concern is related to the type of outcome you have. Like, this is a relatively continuous outcome without any boundaries or anything. So if I knew that something was not that case, I might be more concerned.
Great.
Yep.
Now, in this case, your plots are using only fixed effects, right?
Correct.
But we know that the predictions in our models also include the random effects.
They can if you ask for them that way.
Oh, okay, great.
The R-square values only include fixed effects ever,
Okay,
because random effects are error terms, and I don't think
Yeah.
it makes sense to include them.
yeah, I agree.
There.
Thank you.
See, we really did it. Can we get like a group clap it out? We finished Unit 4 finally.
Yeah.
I think this is like video part 9 or something we're up to, something like that. And yeah, now you can do homework. Yes, so the things that I fixed in this handout, by the way, with respect to doing homework, I computed slope reliability incorrectly when I had, because I forgot that I'd switched out the binary version into the cluster mean centered version. So I updated this page right here. This is page 9. So that number right here that goes into the formula, that's the variance of the predictor that the random slope is for. So the top of this code, I edited pages 2 and 3 so that I got the variance of those two within cluster predictors that will go into the formula for slope reliability, and that is where they come from.
Thank you.
You're welcome. All right, 145. Thanks for hanging in there, folks. Let me know if you need anything. Do your formative assessment, start your homework, have good weekends. That's an order.